So today we're going to talk about ANOVA, also known as analysis of variance. That's what ANOVA stands for, analysis of variance. This, in addition to t-tests, comprise the statistical tools that I use most often in my own research. Other researchers use regression, correlation analyses a lot more, but most of the stuff that I do involves ANOVAs and t-tests. So let's start talking about ANOVA. I got new batteries, I swear. Just get to our class. Oh man, if this doesn't work, this is going to be a long class. All right. So imagine we want to see if exposure to different types of media affects support for Hamas in Palestine. So given the recent renewal of tensions between Israel and Palestine, this is something that's potentially fairly interesting question that some of you may want to address. So imagine if you want to see if exposure to different types of media affect things. Right? People are posting things on Twitter. I'm getting a ton of pictures on Facebook. Both pro-Israeli and also pro-Palestinian. So do these things have effect on people? So we could imagine a situation where we're going to sample some people and show them different types of media. So we could give one sample, we could show them pictures of dead kids and say that these are kids, Israeli children. And these kids, they're dead because of the fighting recently, and Hamas is the cause. So we could show one sample of that. We could show another sample of people, exactly the same picture, but with a different caption, right? And say that these kids were actually killed by the Israeli Defense Force, right? So potentially, just by changing the caption, we could change how people perceive these, and this potentially could affect people's support for Hamas. So we have some manipulation, and then finally we need some dependent variable, right? We need to figure out how much people support Hamas. So we could give both groups of individuals a questionnaire then, after we show them the pictures, measuring their support for Hamas. All right, so imagine that these are our data. The data that I have here, these are made up by me. These are hypothetical data. I made them so they work very well for the test we're going to do today. So normally data won't be this clean. But imagine I took 2 samples of 3 individuals, right? So I got one sample of 3. I showed them the picture, and this group, the Israeli, this is with the caption that says this is an Israeli child. And I took another group of 3, showed them the picture, and said this is a Palestinian child. All right? So I have scores on my support for Hamas member. And the ones that saw the Israeli child, they scored 7, 8, and 9. And the ones that saw the Palestinian child reported 13, 12, and 11. So we can ask some questions like, what's the grand mean? So the grand mean is just the mean of all of our observations. So how do we find the grand mean? What do? We add all of the scores up, right? And then divide by 6. Right. So we have 7 plus 8 plus 9 plus 13 plus 12 plus 11 divided by 6. Oh, it worked. So we have 60 divided by 6, and that's 10. If you looked at this, you could have very quickly figured out that they were centered around 10. But yeah, so the grand mean is 10. Now what are the sample means? Now this, I'm not interested in all of the data. I'm interested in the data for one sample and the data then for a different sample. So for the Israeli sample, their mean is 8, right? 7, 8, 9. Well, 7 and 9 are both around 8, equally far, so it's going to be 8. But if it wasn't so obvious, we just add them up. 7 plus 8 plus 9, all over 3, well that's 24, divided by 3, that's 8. All right, the mean for Palestinian? 12, right? So we have 12 here in the middle, 11 and 13 both equally far away. If it wasn't so obvious, just add up 13 plus 12, it's 11. which is 36, divide that by 3, 12. Okay, so now we have our grand mean, and we have our sample means. So we can ask, like, what's an effect of the manipulation? So if I were to word this otherwise, we could say, like, okay, we know the grand mean is 10. If we know that someone saw, like, the Israeli picture, like, what type of effect did that have? Did that increase their score? Did that decrease their score? How much? So what's the effect of seeing this picture? The grand mean is 10, right? The mean for, the sample mean for the Israeli group is 8. So basically, by seeing the Israeli picture, it's like you have the grand mean, but then you shift people down by 2, right? So we can figure out the effects of the manipulation by subtracting the grand mean from the sample means. So 8 minus 10, negative 2. Palestinian, it would be plus 2, right? It would be 12 minus 10, plus 2. Okay, great. Now, we can rewrite each score as the grand mean plus the effect of the manipulation plus the effects of all the other things that affect individual scores. Let's do an example to make this clear. Okay, we'll call these last things the effects of all the other things that affect individual scores. Call these things error. Remember, like 2 classes ago, we were talking about Aisha and Roll and Ramza. We said, like, well, why are their scores different? Well, one of them studied more. One got a good night's sleep. One got a little lucky. Stuff like this, right? And that's just error. So the Israeli sample, we observed 7, an 8, and a 9. So if we rewrote each score as the grand mean, we would start with what? What's the grand mean? 10. So we're going to start with 10. So imagine that we didn't know what group that they were in, and we just said, okay, what do you guess this person's score is? What's the best guess? What would be the grand mean, right? So we start with a 10. But now we know, aha, they saw the Israeli picture. So what do we know about individuals that saw the Israeli picture? On average, they are 8. They are 8. They are 2 less than the grand mean. So we have the grand mean 10 minus 2, the effect of seeing the Israeli picture, plus error, right? So we can rewrite it as 10 is the grand mean plus negative 2 minus 2, which then gives us the mean for the Israeli group, and then plus minus 1. Basically, this person's error. Does that make sense? Imagine some test for my class. The average is a 75, right? So if I ask you what someone got and you don't know anything about them, you'd say 75. Let's say let's see. Over here is lower, over here is higher. So you know that they're a hard worker, this person. So this pushes their score up. You know that they got a good night's sleep. That would push the score up, right? If you took into account all the effects of these other things, they're intelligent. That pushes the score up. But they drank alcohol right before they came to class. Pushes their score down, right? So basically you have all of these potential variables pushing things up and down. Some of these we're measuring. So here we're measuring the effect of the manipulation, right? We're not measuring their intelligence. We're not measuring their political orientation. We're not measuring their gender. We're not measuring any of these other things, right? So this just all lumps together into error. So for this person, if we write it as the grand mean, again, with plus the effect of the manipulation plus their error, we'd have something like this, right? Grand mean 10 minus 2 because they saw the Israeli picture, minus 0. Error. 0 error for them. This one, 10 minus 2 plus 1. And we can do the same thing for Palestinian, right? So those are the data. So what would this be as an expression like this? It would be 10 plus 2 plus 1, right? 10 plus 2 minus 0, 10 plus 2 minus 4. Does that make sense? All right. So now we can ask, when we look at the scores like this, why do the scores vary? I mean, there's variability in the scores, right? Some are high, some are low. Why?
Because people are different. Yeah.
People are different. What type of the variance is that?
Descriptive. No. Inference.
We can use it as inferential. It's originally a descriptive that we used for inferential purposes.
Independent?
Oh, you're like jumping ahead of me. It is, yeah. Hold that for later. So, what did I say? All of the effects that we're not measuring, that we're not looking at specifically, are called. So that's going to be error, right? So the scores vary because of error, right? That's these parts, plus 1 or minus 1, 0, plus 1. 1, 0, minus 1, right? Scores are varying because of the error. That's due to individual differences in people, right? Why else are the scores varying? So part of the reason that the scores are varying is because of error. What's the other reason that scores are varying? Well, the grand mean is actually the same in all of these, right? There's no variation in the grand mean. That's the same.
Sample mean.
So there's variations depending on which group you were in, on which sample you were in, right? So we have variations due to individual differences, random error that creates variation. We also have variations depending on which group that you're in, right? So the ones that saw the Israeli picture, their support goes down. The ones that saw the Palestinian picture, their support goes up, at least numerically. We haven't run any statistics yet, so maybe this is not a statistically significant difference, right? We need to test that out. Okay, so they vary because of the manipulation, and they also vary because of error. All right, so we have two sources for variations in these scores, the manipulation and also the error. Now, the next question is, how do these scores vary? Do the variations due to the manipulation depend on the variations due to error? No, they don't. Were you saying yes, they do?
Yes.
Yes?
It's the other way.
No? So you're saying no? So we have males versus females. 2 males will say no. 2 females say yes. Anyone else want to jump on board? Let's think about this a different way. Let's think about the conditional probability. If I know someone's variation due to the sample that they're in, do I know their variation in error?
No.
I don't, right? So I have 3 people with a -2. Do I know what their error is? No, I have +1, 0, or sorry, -1, 0, +1. Here, they're +2, and again, I have 1, 0, and -1. So just by knowing one, I don't know what the other one is. I could do the opposite conditional probability, right? Given that the person got a -1 for their error part of the variation, what's the variation of the effect? What's the variation of the manipulation? You don't know. Could be 2, could be -2. This means the types of variances are, now you can answer, independent. That's exactly right. So these variations are independent of one another. They're not connected to one another in any way, right? Now, what do we know about independent variance?
React.
Independent variance adds. Cool. This is the whole idea behind ANOVA. So we have different types of variance. We have variance of the effects. We have variance of the errors, right? So the variance of the effects, these are non-random, right? So everyone in the Israeli group had a -2. Everyone in the Palestinian group had a +2. It's not random. On the other hand, the error variance is random, right? Just by something is non-random and we know something else is random, or even if we know, I guess it doesn't matter what the first thing is. If you know that the second thing is random, then there shouldn't be a correlation between the two. And remember, so last class we talked about independence and correlation, and if something is truly independent, then there is no correlation. All right. So we have variance of effects, which are non-random, the variance of error, which is random. If the variance of effects is non-random and the variance of error is random, then we know that they're independent. They should add. Okay. So we can create a formula for our variance. So the total variance, that would be sort of like the variance in all the scores, kind of like the grand mean, the grand variance. Although no one calls it the grand variance to my knowledge, so we'll just stick with total variance. So the total variance should be equal to the variance of the effects plus the variance of the errors. Does that make sense? All right. This means we should be able to take our total variance and divide it up into parts. Parts for the effects and parts for the errors. So let's go back to our example. So we have our two groups, Israeli, Palestinian. What's the total variance? This would be the variations of all of these around the grand mean. So we need the grand mean to do this. What's the grand mean? You guys remember? 10. So the grand mean is 10. So what's our formula to get the variance? We're going to subtract
10 plus effect plus the error.
the effect plus the error.
Effect variance
Uh-huh.
plus effect error.
Right, but if we want to do that, we'd have to find out what the effect variance was and then the error variance,
Yes.
and then add those two together. We're going to start with the total variance. What's the formula for variance?
7 degrees of freedom. Like we had this one.
I mean, the sum of
Combination.
sum of x minus 10
Okay.
on 10 divided by 10. Square divided by 10.
Yes.
Right? And this would give us a biased estimate, right? Let's work with the biased estimate for right now. All right. So, what is this? What's this? So this is the deviation, right? Deviation score. So what's our deviation score here?
Minus
3.
Minus 3.
Minus 2.
Minus 2.
Minus 1.
Minus 1.
Plus 3.
Plus 3.
Plus 2.
Plus 2.
1.
Plus 1. So if we square all these, what do we get?
9.
9.
4. 1. 9, 4, 1.
What do those add up to? We need to sum those. 28. So 9 plus 1, that's 10, plus 4, that's 14. We've got 2 of those. So 28 over what? 28 over
6.
over 6. 28 over 6. That's good. Awesome. So this is 4.66 repeating. 4 2/3. That's our total variance. Okay? All right. What's our error variance? Now, remember when we were talking about breaking each person's score up? We said, okay, each person's score represents the total mean minus the effect of that particular manipulation, plus the effect of that manipulation, plus the error, right? So if you were talking about the error variance, so you're talking about this last plus the error, versus those other two things. So those other two things was the effect, the grand mean, plus the effect in question, right? So we have the grand mean, which is 10, and the Israeli mean is 8, and the Palestinian mean is 12. So what we're going to do when we create our deviations, we're not going to create the deviations around the grand mean. Instead, we're going to create the deviations around the sample mean. Okay? So we're going to use a different sample mean here and a different sample mean there, right? We'll use 8 over here, and we'll use 12 over here. Okay, so we've got our formula. So what do we have?
Minus 1.
Minus 1.
0, 1. 1 minus 0, 0 minus
Okay, let's square them.
1, 0, 1. 1, 0, 1.
What is it, right? So we add those up. 4.
Divide by 6.
Divide by 6. So what's that?
Point.
Point. It's 2/3.
Aren't we supposed to do them separately, like 2 by 3, 2 by 3, because we have to.
Do we have to do them separately?
Because, I mean, you separate the two variants, the two.
Okay.
So what do you have to mention? The same answer?
So the question is, so I did it like this, right? And I got, sorry, 4/6, which is 2/3. So 0.666. So his question is, instead, should we do something like, let's just do it with these. So 1 plus 0 plus 1 over 3,
Plus.
like that, plus 1 plus 0 plus 1 over 3, right? Is it going to be the same?
No, no.
It wouldn't be the same.
It wouldn't hide.
What would this be? So this would be 2/3 plus 2/3.
4 divided by
So that would be 4/3 and not 4/6. So what's wrong with this calculation? Well, think about when we were doing the independent t-tests and we wanted to pool the variance, right? So we said when the sample sizes were equal, we could just add the variances together and divide by 2. So if we did that, these are the variances added together. If then we took this and divided that by 2, then we have the same answer, right? So yes, you could get it either way as long as you take into account how you need to put those together, okay? All right, so we had the total variance, which was what?
4.6.
4.66, repeating. And we have the error variance, which is 0.66, repeating. So what should the effect variance be?
Related minus will subtract.
We'll subtract what?
This score
Yeah?
from 4 points.
So 4.66 minus 0.66
It should be 4.
should be 4. So the effect variance should be 4, right? Let's see if it is. All right, so the effect variance. What's the effect variance? Well, we have the grand mean and the individual sample means. Now, the effect variance is basically just the variance of the sample means around the grand means. So remember how we had these things written 10 plus, or this is actually minus 2, minus 1, 10 minus 2 plus 0, 10 minus 2 plus 1, like that.
Yeah.
So in here, now we're not interested in the error. Instead, we're interested in the effects, right? So we can get rid of the error. So this is just 8, 8, and 8, right? And similarly, this would be 12, 12, 12, right? So for each score, we basically have the sample mean as part of that score, then plus some error. So we've already figured out what the error variance is, so now we want to figure out what that effect variance is. So all we need to do is compare the sample means to the grand mean. So what are our differences now? So 8 minus 10 is negative 2, negative 2, negative 2. These will be 2, 2, 2, and the squares will be 4, 4, 4, 4, 4, 4. So we add all of those up. Will be 4 times 6? 24 divided by 6? 4. Yeah, cool. So it all adds up. So the variance, our total variance, we were able to break it down into 2 parts, right? Part that was due to the effects, 4, and part that was due to the error, 0.66. Repeat. Cool. All right. Now, these pieces of the variance that we have, these were our biased estimates of the variance, right? Now, we're not going to want to use the biased estimates of the variance. We're going to want to use the unbiased estimates of the variance. Okay, so the unbiased estimate of the variance, we had this on the top, right? This is the sum of squares. And we had what on the bottom? N minus 1. This was the degrees of freedom, right? N minus 1 was the degrees of freedom. So basically, to get our unbiased estimate of the variance, we took the sum of squares and divided it by the degrees of freedom. Okay, so we have the sum of squares on top, the degrees of freedom on the bottom, and dividing the sum of squares by the degrees of freedom gives us the mean squares, the unbiased mean squares. All right, so let's take a look at our mean squares, our sums of squares, and our degrees of freedom. So total. You guys remember what our total sum of squares was?
0.
Wasn't 0.
Mean 6.
Well, our variance that we estimated was 4.66, right?
Yes.
It was 28 divided by 6. So the 28, that was our sum of squares,
Yeah.
right? And we divided by 6, but we shouldn't have if we want to get the unbiased estimate. What should we divide?
Plus 5.
5, right? 5. This is just n1 plus n2 minus 1, right? Because when we're getting the grand mean, we had 6 pieces of information. We can set the first 5 to whatever we want, but once those first 5 are set, that last one is set. So for the grand mean, or the total, we have 5 degrees of freedom, right? So what's the mean squares? 28 divided by 5, right? And that's 5.6. All right, Ruby. So our total sum of squares is 28. Our total degrees of freedom is 5. Our mean squares is 5.6. Now there's something I want you guys to pay attention to. 1, the sum of squares total will equal the sum of squares of the error plus the sum of the squares of the effect. Okay? The other thing I want you to pay attention to is the degrees of freedom. The degrees of freedom total will equal, what do you think?
5.
But not expressing them as 5. Expressing them as...
Sample size minus 1.
Okay.
The total sample size.
Total sample size minus 1. But what I'm looking for is something that has to do with the degrees of freedom for the effect and the degrees of freedom for the error. So the sum of squares total was, or should be, the sum of squares of the error plus the sum of squares for the effect, right? So if that same type of thing happens, if we have degrees of freedom total, what should the degrees of freedom equal in terms of degrees of freedom for the error and the effect?
Degrees of freedom effect.
For the effect, okay.
And for the error.
So total equals sum of squares error plus sum of squares effect. And degrees of freedom total should equal degrees of freedom error plus degrees of freedom effect.
Plus 1.
Equal.
Plus 1.
Equal?
Yes.
Where?
Degrees of freedom.
Here? These should all equal one another.
Yes.
Yes.
No.
No?
We should plus add them and minus
equals
1. No, equal.
Well, if it follows this pattern,
It should be added.
then it should be this.
Yes.
If it doesn't follow that pattern, maybe it will be this.
Not this.
It's not. It's equal.
We'll see. We'll see. We have 2 possibilities. All right. So, sum of our squares for our error. You guys remember what that was? We had 101, 101, 4. So that should be 4. Okay. How many degrees of freedom do we have?
5.
She says we have 5.
Yes.
How many do you think we have?
We have 5. Because there were 6.
There were 6.
Yes. For error.
So if you have 6, then you just subtract 1 and you've got 5, right?
Yes.
That's 5. That's actually not correct here.
Because we have 2 samples.
We have 2 samples. We have 2 samples, right?
We subtract 1 from each.
Yeah.
We need to subtract 1 from each. So what will our degrees of freedom be?
4.
Minus 2.
4. So that would be all of the n1 plus n2 minus 2. n1 plus n2 minus 2. That sounds familiar.
Yes, it's the same from the independent.
It's the same as the independent t-test. It's the same as the independent t-test. n1 plus n2 minus 2. We're estimating 2 sample means from 6 pieces of data, right? So, if we're looking at 1 sample, the first 2 things are free to vary, but then that 3rd one is set. And same thing for the 2nd sample. So we don't really have 5 degrees of freedom, we have 4, right? So what's a mean squared?
1.
Yeah, this is easy. 4 divided by 4, 1. Good. Okay, so what should our degrees of freedom for the effect be? So we had our df total was 5, and our degrees of freedom for the error was 4. What should our degrees of freedom for the effect be? 1.
If you put it in the same way, it would be 1. No, I mean, it's different. It should be also 4.
It should also be 4. Actually, it should be 5,
5.
like she was saying.
Yes, it should be 5.
So we have 3 different
I don't
possibilities.
understand the question.
5, 4, or 1. It's one of those. I just said the answer, actually. It's 1.
Yeah, it's 1.
It's 1.
We do it now.
So we'll figure out why in just a second. All right, so the effect. What's our sum of squares?
12.
Was 24, right? 24. Now we had 28 for the total, and we had how much
4.
before?
Minus 4.
So plus, I'm sorry, you're right, minus 4. That should leave us with 24. And if you go back, we can go back. 24. Sum of squares over our sample size. But we're not going to use the sample size. We're going to use the degrees of freedom. So, what is it? I said it was 1. Why is it 1?
5 minus 4.
5 minus 4. We have 5 degrees of freedom total.
And error?
4 of those 5 degrees of freedom were for our error.
1.
So there's only 1 degree of freedom left, right? So that's the effect. But we can also think about this a different way. Yeah.
Because when we did the 24, we calculated them anyway. But when you want to calculate the degrees of freedom, doesn't give us 1, it gives us something else.
But
It gives us something else. So let me put a little more up here, and then we'll see if you get it. So I said k minus 1. K, what's k? K is like the number of samples that you have. You have 2 samples, right? Now, let's think about this. So, we have 2 levels, Israeli and Palestinian. And we know what the grand mean is, right? The grand mean is 10. So, if we don't know what either of these are, one of them is free to vary. Israeli could be -2. It could be 25. It could be whatever. But once you set that mean for Israeli, and you know the grand mean, the other one is set. You know what the other mean is. Does that make sense? So remember when we were calculating the variance for the effect. So we worked with 8, 8, 8, 12, 12, 12. We were basically repeating the same means a bunch of times, right? So we really don't have 6 things that are varying. We only have two things, right? And once we know the one, we know the other, because we know the magnitude. So, for the effect, we have 1 degree of freedom. So what is our mean square? 24. 24 divided by 1, 24. All right, groovy. So, now ANOVA, an analysis of variance. Instead of using a t-statistic, you're going to use an F-statistic. So F is comparing the variance of the effect to the variance of the error. And it uses a ratio to do this. So F is basically the mean squares of the effect, all divided by the mean squares of the error. Okay? Now, let's think about what this is telling us. What is this telling us? And the mean squares are basically like a variance of the effect plus a variance of the error.
It shows us how the error affects the whole variance.
It kind of shows us a proportion, like how much of the total is related to the error versus the effect, right? But it's not the mean squares total on the bottom. So it's not just the effect of, or the variance of the effect compared to the total. It's the mean square of the effect compared to the mean square of the error. Now let's imagine that you have like basically no effect. There's no effect. Right? So you're going to have some mean square. And it will be close to 1. If the means are basically the same, then that mean square is going to be very close to 0, right? So when there's basically no variance due to the effect, that should be fairly close to 0, right? Now, how much variance is there due to the error? What could it be? What does variance range from? Goes from, what's the minimum variance something could have?
0.
0 is the minimum variance something could have. What's the maximum variance something could have?
No, not 1.
Not 1.
Infinite.
It could be infinite. So variance could range from 0 to infinity. So we're looking at the variance of the effect and the variance of the error. If we have basically a 0 up here, we're going to have 0 for F. Unless we have also 0 for the error, in which we're going to have a weird situation. This will practically never happen in the real world. Thank goodness. Okay, so normally, this won't be 0. It might be close. But now think, what if we have an effect? Something that actually has some variance, right? Now, if this is really big, if there's a lot of variance in the overall samples, and there's not much variance due to that, it might be that it's just error, it's just by chance, right? But if instead you have a huge amount of variance due to the effect, and only tiny variations due to error, then that's probably an indication that you have something real. Yeah? Well, if we create the F distribution, then we could potentially talk about confidence. We could create confidence intervals and things. The probability of observing something in F that extreme or more, right? Okay, so let's take a look at the sampling distributions of F. Thanks for bringing that up. But before we do this, let's take a quick look at the sampling distributions of variance, since the sampling distribution of F is based on sampling distributions of variance. So, sampling distribution of variance. We've already sort of covered this twice in this class. So in the second class, where we looked at the distribution of absolute differences, we were looking at the central limit theorem. We saw something, it wasn't the square differences, it was the absolute differences, but it has the same, or a similar type of shape. Also, in the 10th class, we looked at estimating parameters, and we talked about how this formula with just the n gave us a biased estimate of the population variance. And we saw how to change our estimate to give us an unbiased estimate. So let's take a look at what we did in the 10th class. Do you guys remember these? So these We took, I think, 10,000 samples. So for each sample, we calculated the variance. And we had a sample size 2. So for each sample, we took a variance, and then we created a histogram based on all of those 10,000 samples. And we see something that looks sort of like that, right? We also did it for 4. And this one isn't quite as steep. This one is a bit more shallow, right? We could do it for 10, we could do it for any number. I don't think we did it for 30. I was looking at the slides, and I think 4 was the most. I don't know. We'll do 30. Or actually, we'll do 30. Okay, so the chi-square distribution. The chi-square distribution is actually the distribution, not of the variance, but of the sum of squares. And the variance is the sum of squares divided by the degrees of freedom, right? So the chi-square distribution is the probability density for the sum of squares from a standard normal population. That is a normal population with a mean 0 and a variance of 1. So the chi-square distribution depends on the degrees of freedom. So here, notice that as the sample size goes up, also the degrees of freedom is going to go up. Here we have degrees of freedom equal 1. Here we have degrees of freedom equal 3, right? So as the degrees of freedom go up, we see a change. So the chi-square distribution, we need to assume that the populations we're sampling from are normal, right? Because this is based off of the standard normal population. And we're going to need to make this assumption for doing the ANOVAs, since the ANOVAs are based on this distribution. Okay, or if we have a large enough sample size. Now, this is going to range from 0 to positive infinity, as we've already established. Sum of squares can be negative, right? Unless you have an I in there. But we're not dealing with imaginary numbers in this class, thank goodness. All right, so let's look at some chi-square distributions. So here is degrees of freedom equal 1. So this is similar to our sample size 2 that was before. Pardon?
Degrees of freedom is infinite.
When the degrees of freedom is infinite, then this will become normal in shape. Okay? Kind of like the binomial. The normal is amazing. Like, as the sample size gets large, the binomial looks like the normal, sample size gets large, chi-square looks like the normal, sample size gets large, the F is also going to look normal. Okay, anyway, so this is with degrees of freedom 1, not infinity, just 1. With degrees of freedom 2, this tail is getting a bit smaller. Degrees of freedom 3. Whoop, now we switched. We have this hump here. Degrees of freedom 4. Degrees of freedom 10. Did I do 30 or did I do 20? Oh, 20. I did 20. So this would go like that. And it starts getting a slightly more normal shape as the degrees of freedom go up and up and up. Okay, so these are our chi-square distributions. Now F.
So what's the difference between that distribution and F again? So we can do that.
So what's the difference between chi-square and F? F shows us basically here, so these are probability densities. The probability density of observing a sum of squares equal to 5, equal to 10. Now the F is a ratio of the mean squares. It's the sum of squares divided by the degrees of freedom, and the sum of squares divided by the degrees of freedom. Right now the chi-square depends on the degrees of freedom. So we're basically looking at some sum of squares for some degrees of freedom, right? Now the F, instead of just looking at one sum of squares for one particular degree of freedom, we're looking at two sums of squares for two different degrees of freedom. Does that make sense? Taking the ratio of those two. So F equals mean square effect over mean square error.
Okay, but X2, which mean does it involve? Which, let's say, variance does it involve? Which squares does it involve?
So this could involve the variance for either of these. So both of these are associated with a particular chi-square. So the mean squares for the effect, we said we had 1 degree of freedom. So for this particular sample, we're looking at a chi-square distribution like this for the numerator. For the denominator, the mean squares error was the sum of squares for 4 degrees of freedom, right? So 4 degrees of freedom, that's the green one, that's this. So F is now going to be comparing sort of this, dividing this by that. Give. All right, so F. We have each mean square is just the sum of squares distributed as a chi-square with the appropriate degrees of freedom. Now F is a ratio of the mean squares. That's this, right? So the distribution of F is going to show us the probability density for different values that this could take on. Now we saw that this could take on any of those values if we standardize the distribution, right? Set the variance equal to 1 and the mean equal to 0, by basically taking z-squared of everything. And this, lost my train of thought, you can go on. So this is also going to range from 0 to positive infinity, right? Because this can only be 0 or infinite, and this can be 0 or infinite. We're not dividing by anything negative, so we're also going to have something that goes from 0 to positive infinity. Now this is going to depend on a pair of degrees of freedom, not just one. So the chi-square depended on 1 degree of freedom, but now this is like 2 chi-squares. So we have some degrees of freedom for this, some degrees of freedom for that. So I have the degrees of freedom for the effect, and degrees of freedom for the error. So let's look at some F distributions. Now, as the degrees of freedom increase, there's going to be less mass in the tails. So let's see. Okay, so this is an F with 1 degree of freedom on the top, 2 degrees of freedom on the bottom. And it looks something like this. It's very similar to the chi-square, right? This is an F with 1 degree of freedom on the top, 4 degrees of freedom on the bottom. Now, they're both pretty close, but notice how this crosses over down here. This tail, there's a little bit less mass in the tail. This is F130. Again, very, very close. So even if you did like F1 500, it's still pretty close. It doesn't really increase that much. But now let's change the initial degrees of freedom. Okay, let's leave the second bit of degrees of freedom as 30 and change the initial. So let's use 2. Well, when we had 2 degrees of freedom for the numerator, you see up here, it crosses over on this side, so there's less mass over here. Also, it crosses over down here. There's less mass here. We have more in the middle. As we go up, F4, 30. Now we have very little at this tail, a little bit less in this tail, and a lot more right there. F10, 30. Again, very little in the tails, a lot more in the middle. So these are our F distributions. And there are an infinite number of F distributions, because you can have infinite number of degrees of freedom. If you had an infinite number of degrees of freedom for both, what distribution would you have? If you had an F with an infinite degrees of freedom for both the numerator and the denominator, what distribution would you have? Normal. All right, so for previous 2 tail tests, we were interested in extreme values in either tail, right? So we would draw a distribution like this, and we would say, okay, if we find something that's over here or something that's over here, we're going to reject, right? Now, this is different for the F. Since we have this ratio, when will F be 0? When will F fall in this tail with very little mass? Let me draw it to make it look more like that.
When the effect degrees?
It will be 0.
When there's no effect. So this will be 0 when there's no effect. But we're doing statistics to see if there is an effect, right? So if we get a 0 when there's actually no effect, then we really don't care about this tail. We're not going to find critical values over here. It doesn't mean anything in terms of the effect. It means there's no effect, right? So we only are going to want to reject when we have something over there far enough. So we're only going to be interested in one of the tails of the F distribution. So this will make things a bit easier for you because you only need to calculate one critical value instead of potentially 2. All right. So since we're only interested in one tail, and since the sum of squares doesn't tell us which mean is larger, we are going to stick with directionless hypotheses. We're not going to be able to say, like, the mean of Israeli is greater than the mean of Palestinian. We're just going to say they're equal. So a null hypothesis of equality. So we can write it like this. The mean of Israeli minus the mean of Palestinian equals 0. Or like this, which is similar. Mean for Israeli is equal to the mean of Palestinian, right? Why? Why are we doing this?
Some square doesn't tell us which mean is larger. We cannot determine which direction to go.
Yeah, so the sum of squares has no idea what's larger or smaller. It just knows how much variability there is for that effect. Now, for something like this, hold on. So I'll answer this question a bit later, I hope. All right. So this should seem similar. So when we were dealing with the normal distribution, we used d norm. We gave it some parameters. And what did d norm give us? Gave us the density. df, that's going to give us density for what distribution? For the F distribution, right? Now, it will give us the density for some value of F, for that F ratio. Give us the density for that value for some degrees of freedom for the effect and some degrees of freedom for the error. Remember how the distribution of F depended on both of these things. This is why we need to give it both the degrees of freedom for the effect and also the degrees of freedom for the error. So we can use df, give it the F ratio that we're interested in, give it the degrees of freedom for the effect, or the numerator, and the degrees of freedom for the error, or the denominator, and we'll get the probability density. PF, what should PF give us? Cumulative probabilities. PF is like P norm. P norm gave us cumulative probabilities for normal. PF is going to give us cumulative probabilities for F. So we say, what's the cumulative probability up to this F ratio for this degrees of freedom for the effect, this degrees of freedom for the error? This is going to be useful for finding p-value. Someone set p-value, right? And we can use our cumulative probability distributions to figure out what the p-values are. So we're going to do the same type of thing here to find p-values. QF. Quantile. So this will, sorry, that should not be F rat. It should be some percent that we want to cut off, right? We want to cut off 95%, right? Our alpha is 0.05. So what is the value of F for this degrees of freedom in the numerator, this degrees of freedom in the denominator, that cuts off 95% of that distribution? Right? What will that tell us? So that will give us the value of F. What do we use that F for?
Find out the ratio when there is 5% for the unknowns.
Right, and what do we call that? It's a critical value. Yeah. So this will be useful for finding critical values for F.
So you said the hypothesis should be non-directional.
Non-directional. Just these means are equal.
Can you say something that it's going to be easier for us when we calculate because it's going to be, we need to calculate one critical value or not?
Well, so if we go back to the distribution, it looks something like that. This is 0, positive infinity is way over, not positive infinity. It's over there somewhere. Now, we're only going to have values close to 0 when that mean squares effect is close to 0, meaning that like there's basically no effect. So since this tail is an indication of, like if you think about it, if you cut off the 0.25% down there, like that would be where there's so little variation in this that it's unusual. Because you expect some variation, right? So that would mean that something is odd. Something is unusual, but it doesn't mean that you have a significant effect. Okay? The significant effect is over here somewhere. When this is not 0, when this is positive, and when the thing beneath it is smaller. Yeah?
So we have not a original hypothesis, but we're interested in one critical value here.
That's right. It's a non-directional hypothesis, but we're only finding one critical value. So that is different from the t, because with the t, we found 2 critical values for our non-directional hypothesis. Here, we can't have the directional hypothesis because, hold on, we'll get to this in a little bit.
Are we going to find lower critical value once?
No, you only find one critical value, and that's the upper critical value. There is no lower critical value.
Because when we say values?
Because if you find the value down here, the quantile that cuts off the bottom 2.5%, the bottom 1% or whatever your alpha is, half of that, that actually would only happen when you basically have no effect at all.
So if you have like alpha is 0.05, what will you use here?
What would you use if alpha was 0.05? If alpha was 0.5 or 0.05, you would use 2f 0.95, and then the degrees of freedom. So here we have 1 degree of freedom and 4. Okay? All right. So back to our example. Okay, so we found our sum of squares for the effect. It was 24. We found the sum of squares, or the degrees of freedom for our effect, that was 1. The mean square was 24 divided by 1, 24. We found the sum of squares for our error, that was 4. We found the degrees of freedom for our error, which also was 4. 4 divided by 4 is 1. That was the mean square for our error. So, what is our f going to be? F is the ratio of the mean squares. 24 over 1. 24. Boy, that math is easy. Okay, so there is our F-statistic. This is the value of F that we observed, or observed. Alpha 0.05. So we want to find our critical value, QF 0.95 on 4, exactly what we figured out last slide. And that's 7.70 lit. What do we do?
Okay, we find 24.
So
We
7.0.
found the P for 24.
We don't even need to find the P to decide what we need to do. We reject, right? This was our critical value. Anything that falls beyond that, this over here, this contains 5%. So 24 is like way over there, right? So we should reject. Yay, reject the number. Okay, now you want to find the P value. Ruby. 1 minus PF 24, the F that we actually observed, and then the same degrees of freedom that we used here. What is it? 0.008 stuff. Is that less than 0.05?
Yes.
Yes. We reject. Great. All right. So why didn't we do an independent t-test? I mean, we had two samples, right? Two independent samples. We could have done an independent t-test.
Because the differences, I mean, there are not much different effects in.
There are much different effects here.
Then we're not doing paired anyway.
There was such a different effect here that it was significant.
About error?
It's like the mean. It's like after studying before, like the samples to samples, the picture are the same.
So the pictures, I use the same picture as a control. If you're going to do an experiment, you want to control things as much as you can. So if you use the same picture, you are controlling things. You're only changing the caption, right? So that's a form of control. But we still have some effect, and we could address whether or not there's an effect with the t-test, right? With an independent t-test. Yes?
I think it's about error. That when we find the error, we use like degrees of freedom. We use pair test. Like what we used for pair, like.
But we had a bunch of different types of t-tests. We had the one sample t-test. We had the two sample independent t-test. And then we had the paired, right? But this, I didn't say anything about pairing either. I didn't say like, oh, let's subtract the Israeli from the Palestinian or any of that stuff, right? So this isn't paired. This is like an independent t-test. This is exactly like the independent t-test. We could have used it here. As it says up there, we could have. So let's do it. Let's do the independent t-test. So, we can specify our data. Example 1 is that. Sample 2 is this. Then we can use our handy-dandy t-test function. T-test, sample 1, sample 2. Set the variance is equal. Right? Boom! This is what we get. What do we see?
Is it the same? P-value is like T-value?
P-value is the same. 0.00805. That's what we had here.
And means?
If you rounded that up.
Means or same?
The means are the same.
But confidence interval?
We didn't do a confidence interval. We could if we wanted. I don't think I'm going to ask.
No. So we reject it.
We don't reject here?
No,
Yeah, we would reject here as well, right? So the identical, the p-value is identical.
So
And does someone have a calculator?
Yes.
How about a computer with a calculator? You have a calculator. Oh, wow. Oh, it's a phone. I was like so impressed. Okay, can you take 24, that was our F statistic, right? 24, and take the square root of that. Square root of 24.
4.89.
4 point what?
8989.
F is just t squared.
T
T-squared. Right? The t, we have this like, the effect on the top, and we have this standard error, which is like the square root of the variance, some function of that, right? It turns out that for this type of test, we get exactly the same answer with F or with t. Same p-values, and F is just t squared. So, if F is just t squared, why do I even bother teaching F?
Yeah.
That's a good question. Why are you wasting our time on that? Well, you can do directional hypotheses with t-tests, right? So F actually kind of sucks. Because it's like hard to do. Harder to do. So, did I just waste your time? What do you got? If I'm a good teacher, I didn't waste your time. Hopefully this is not a waste. Unlike t, you're not limited to comparing two means. So t, you can look at one mean compared to some hypothesized value, or you can look at two means, but that's it. We didn't create anything where you could like look at 3 or 4 or 5 or 6 or whatever. T doesn't have that capability. F does. F rules. So imagine that we have our third group now. Right? So we have Israeli, Palestinian, and control. They didn't actually see any pictures. We just gave them the support form, right, that they filled out. And we have those data. Okay, so so we don't have a lot of time, so I'm going to sort of fly through some of this. So again, the grand mean is 10, because I just centered this control around 10. So I didn't have to mess things up too much. The Israeli mean is the same as it was before, the Palestinian mean is the same as it was before, and the mean of the control is 10. So the sum of the squares total, we just want to add up each of these differences from the grand mean. So this is 3 less, this is 2 less, this is 1 less, this, where did I think I put in the control here, 0 less, 1 less, 1 more, 3 more, 2 more, 1 more, right? So that is 30. So our sum of squares total is 30. Our degrees of freedom total is 8. Yes. N1 plus N2 plus N3 minus 1. Okay, sum of squares error. So now what I'm doing is I am comparing each value in each sample to its own mean. Okay? So the sum of squares for the error, well, this is 1 less, this is 0 less, this is 1 more. I think I did this next, maybe not. Palestinian, this is 1 more, that's 0 more, this is 1 less, 0 more, 1 less, 1 more. 6. How many degrees of freedom do we have? 6. What should the sum of squares for the effect be?
What is the total? I mean, okay, 24.
Should be 24, right? 30 minus 6. All right, well, let's see. Boop, 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 boop. Yeah, it is 24. You can double check the math if you want. Basically, what I am doing is I am saying 8, 8, 8, 12, 12, 12, 10, 10, 10. Each of those minus the grand mean. So minus 2, minus 2, minus 2. I am doing math. 0, 0, 0. Plus 2, plus 2, plus, I'm sorry. 0, 0, 0, plus 2, plus 2, plus 2. Sorry, I got the order. So anyway, that's 24. And how many degrees of freedom do we have? 2. 2 degrees of freedom. We have 3 sample means. 2 of those sample means are free to vary before we know what that third sample mean is, right? That's exactly right. A minus 1. All right, so our F test. So we have the sum of squares for the effect is 24 divided by the degrees of freedom. 24 divided by 2 is 12. Sum of squares of our error, that was 6, divided by degrees of freedom for our error, which was 6. Mean square is 1. So F is equal to 12. 12 divided by 1 is just 12. Alpha again, 0.05, our F crit. Now this is basically the same as it was before, but this has changed. We have 1 more degree of freedom for our numerator. So if we do that, we find out that it is 5.14. We draw our distribution. So here, 5.1. What do? We reject. 12 is out here somewhere. We reject the null. Great. What's our p-value? 1 minus pf12 to 6. 0.008. It's not 0.00805. It's not that. This is actually a little closer to 0.05 than we had previously. Why? Well, part of the reason why is because this numerator is smaller, right? Because we're dividing by more degrees of freedom. So I guess this is a research design issue. If you want to have a lot of power, only look at groups that you are interested in. Don't throw in everything. Don't look at, okay, here's Albanian and Israeli, and this is American and Palestinian and nothing. You throw in all of those things and you end up having some large number of degrees of freedom for the bottom, and then this is going to get tiny. Okay? Okay, so interpreting the F test. When you reject the null, when you're comparing 3 or more groups, you can say this. You can say means were not equal. You can say at least one of the means was different than the others. You can say that. You can't say, well, this mean is larger than that one. Because all this is doing is comparing the variance for the effect against the variance of the error. Now, let me put an asterisk here. When you only have 2 means, like we did originally, and you know that the means are significantly different, and you only have 2, Well, the one that's larger has got to be the one that's larger. But when you have 3, it's not necessarily clear, is the, the Palestinian, is that larger than the control? Is that larger than the Israeli? Like, there is some difference, but which is it? It could be all of those means are different from one another. Or it could just be that Israeli is different from Palestinian, and that's the only thing. We're going to need follow-up tests to look at which individual means are different. More on this later. One way to do it is t-tests. Okay, so assumptions of the F-tests. Samples come from a normally distributed population. No biggie when you have sample size 30 or more. Samples come from populations with equivalent variance. This is the same assumption that we made with the independent t-test, so where we're able to set var equals to true. Also that the observations are independent. If you aren't getting independent observations and randomly assigning people different treatments, then that will fail. These are basically the same assumptions that we had for the independent t-test. Also, sample sizes for the different groups should be identical. So notice when I had this, I had 3 Israeli, 3 Palestinian, and 3 control. All the same sample sizes for each of my different groups. That's going to be important. If you don't, then the variance for our error and our effect won't be completely independent. All right, next class we will do factorial.